you do not have to write these all down. Like we're not gonna write the equations down. So I'm gonna give you a handout that has those on them. Okay. However, I would write down the names of these models because I am going to talk about like what types of problems would use each model. Okay. Now, with our application problems, they can get a little long, so probably not going to ask you a ton of these on the test. However, a fast question for me to ask would be, given this situation, which model would I use? Does that make sense? So that's why I said I would at least write down the names. Okay. This is kind of the fun part, right? So like we learn math to be able to apply it to real-world situations and solve real-world problems. And exponentials and logarithms actually have a lot of cool applications that we can use. So for our exponential growth model, a lot of these we can look at is population or sales, okay? But it's going to be with restricted time. Because remember that an exponential growth model, right, it's like exponentially big, yes? And if I'm talking about a real world situation, my population isn't going to get big forever, or my sales aren't going to continue to increase forever. So usually what's going to happen is they'll say, okay, this represents the population between the first and fifth year, okay? Like they'll restrict your time. Okay. Now, some exponential decay models are if we are talking about like death rates, like for if it's hunting season and the cute Bambis are going away, then we could talk about the death rate. Yes? Mm-hmm. Or like the population in time of like a plague. Okay. That would also be a decay model. Another big one that uses R is carbon dating. What is carbon dating? Have we ever heard of carbon dating before?
Definitely heard of it.
Heard of it? Okay, that's good.
I know what it is. I don't know what it is exactly.
Okay.
Is that like a water? Or no, that's Half-Life.
Yeah, so half-lives are also exponentials, and those are for radioactive isotopes. So carbon dating is when you find a fossil, and we want to date how old that fossil is, okay? All living stuff, okay, including like wood or things that aren't necessarily like an animal, including animals, all have carbon in them. And that carbon, after you die, goes down, or it decays and goes away. So we can find out how old something is by taking a sample of it and looking at how much carbon is left in that sample, and basically working it backwards to figure out how old it is. Like that's how they date fossils and things like that. Yeah.
Like how long does it take for all the carbon to be gone? Like to where you wouldn't know how old. You know what I mean?
Depends on the half-life of carbon.
Yeah.
I mean, like, I think there's always still traces of carbon, right? Because think about your exponential decay. Now, it might get to a point where it's so small that it would be too hard to detect. Does that make sense? Mm-hmm. But here, we are looking at something that's getting closer and closer to zero, but we do have a horizontal asymptote at zero. So you might get to a point where there's not enough carbon to be able to detect it, but there will always be trace amounts of carbon.
Wait. I got a question.
Sure.
So I saw this thing one time. I found it quite interesting. So it's like, let's just say Usain Bolt and the turtle are racing, right?
Does this have to do with what we're talking about here?
Yes.
Okay.
Okay, and the turtle gets a 100-meter head start, right?
Okay.
So by the time that Usain Bolt runs that 100 meters, the turtles has already gone 10 meters.
Correct.
But then when Usain Bolt gets that 10 meters, the turtle has gotten to a meter. And then by the time Usain Bolt got to the meter, the turtle has gotten
So yeah, it's like the example that we did in class, right? I had two people that were standing. Technically, right, my person can always go half the distance. It's called one of our mathematical paradoxes, okay? Right, technically I could always go half the distance, right? To where technically, if you want to think about it, mathematically, one item would never reach the other one, because I could always go half the distance, yes? The other would be, traditionally, it's called the tortoise and the hare problem, but yes, technically, if your tortoise is always moving, then your hare is always playing catch up, right? And so, paradoxically, it would never catch the tortoise, but realistically, it does. So there are a couple of things like that that are called your mathematical paradoxes, because we can mathematically show that these things never could happen, but realistically, we know they do. Yes. All right. Next model is your Gaussian model. It's what we call the bell curve, and we use it to look at test scores. So it's gonna look. It's called a bell curve because it looks like a bell. So it's gonna be low on the ends and higher in the middle. So kind of if you think about it, right? You're gonna have a couple of people that probably don't do so hot on a test, like a D or an F. Most of your students are gonna be average, so they're gonna get some C's and B's, and then you're gonna have a few students that do really, really well and get high A's. Yes. So that's kind of what the idea behind a bell curve is. We don't talk a ton about it in here, but if you continue on to statistics, it gets used a lot. So if you take AP statistics or statistics in college, you'll see that a whole lot. So, there you go. The next one is our logistics growth model. It gets used actually a lot more often than our exponential growth model. So it is population with a limiting factor. Okay, this is also the spread of a virus. And the reason why it gets used most often is because, like I said over here, realistically in the real world, our graph is not going to continue to get big forever, right? At some point, if the Bambis are on a piece of land, right? Eventually they're going to run out of space, or they're going to run out of water, or they're not going to have enough food. Yes, so there's going to be a max capacity that the deer could reach. Same thing with the spread of a virus, okay? At some point, I'm not going to have any more people to get infected, or there's going to be some people that are immune. So what happens is that it starts out as an exponential, but then it levels off. So it has what I call the limiting factor at the top. So it has both a horizontal asymptote at the bottom and also a horizontal asymptote at the top. So it has to stay in between those two things.
Wait, so if it's a virus and it's exponential growth or logistic growth, it never touches zero, right?
Correct, because somebody had to be patient 0, right? So you at least had to start at 1 patient. We don't usually talk about the left side of the graph because that would be negative time. So you're going to start at 0, 1. You had to start with 1 patient,
yeah.
right? So yes, again, realistically, we wouldn't look at the left side of the graph.
Mm-hmm.
We would just kind of look at it starting from.
Okay, gotcha.
But if I had 30 people in the classroom, right, and those people were slowly getting infected, it can't technically go above 30, right? So I only have 30 people to get infected. And sometimes, usually, someone's going to be immune from it, or doesn't interact with the people that are getting sick, and so usually it gets really, really close to some number, but it can't go past that. No, good question. And then our last type is our logarithmic models. Okay, those are for we have the Richter scale, which measures earthquakes. We have the pH scale, which measures acidity in chemicals or liquids. You also have measuring decibels or how loud something is. All of those are logarithmic models. Yes, again, you don't have to have, you need to know this top one, okay, for your exponential growth, but the other ones you do not have to have memorized, okay? Now, you do need to know which situation would I use which model, but alright. Let's make us some examples. So here we have the amount S in billions of dollars spent in the United States on mobile online advertising in the year 2010 through 2014 are shown in the table. So just by reading that, okay, we're talking about S, which is money spent, and they give us a restriction on our year. So which of our models would we be looking at? Yeah. So we're talking about money or like expense, and then I'm restricting it to only a certain amount of time. So it is an exponential growth, which is given to us over here. So it is S equals 0.00036 e to the 0.7563 t power. So super fun numbers. But with our application problems, most of the time the numbers aren't super pretty, but they still work like we need them to. So they give us a table and a graph, so you can kind of see the exponential growth happening in our graph. Okay, it says t represents the year, with t equal 10, corresponding to 2010. Compare the values found using the model with the amount shown in the table, and then according to this model, in what year will the amount spent on mobile online advertising be approximately $65 billion? So we're going to do this first part first. So this is I want to compare some values. We're not going to compare all of the values. So we're just going to pick one. Let's not pick the first one, but what year do you want to compare?
2013.
I heard 2012 first, but either one would work. So my model is S equals 0.00036 e to the 0.7563 t power. So if I wanted to know from my model, okay, how much was spent in 2012, what would I do? Why 12 and not 2012?
Because it's
Because it said that t equal 10 corresponding to 2010. So
Cool. Yeah, so I have a unit conversion here. Yes, because most of the time, again, because we're dealing with exponentials, we don't want to plug in 2010 because we would get a really big number. So there's usually going to be some sort of like correspondence onto sizing down the numbers a little bit. Well, why are we plugging it in for t?
where t represents the year.
Yeah, so t is time, that's why it's a t. And we're talking about that is the year, and we want to know how much was spent, which is what s represents. So if I plug that into our calculator, what do we get? 3 point what? Okay, what does that represent? Does it tell us?
billions of dollars.
So it tells us that S is in billions of dollars. Is that fairly close to what they have in the table?
Yeah.
Yeah. Now, the farther that we get away from the start, the farther away my model is going to be from the data that we have, which is why they have to restrict it and say I can only use this until, whatever, 2014. Because after a certain amount of point, it's no longer going to really be very accurate. Are we all okay with that? If I give you a model and I give you a time, we can plug in. Yes? So either find spending or population or something like that. Yes? Okay. Because then on part B, it asks us, according to this model, in what year will the amount spent be approximately $65 billion? So I'm plugging in 65 for
S.
S, and again, we're not using 65 billion because S is in what unit?
Billions.
Billions of dollars. And again, we wouldn't want to plug in 65 billion because that's a lot of zeros. Okay, so it makes it much easier for us to deal with. And then what are we solving for?
T.
And what type of equation do we have?
Exponential
an exponential, which is what we've been practicing. Who would have thought?
Wow.
So what do we need to do first? Divide. And we are going to hold off on plugging this in until the very end. Because it is an exponential growth, which means that if you round too early, you're going to get an even bigger rounding error. So we hold off rounding as much as possible. So then now, how do I undo my e?
Unlog.
Natural log. And then what is our last step going to be?
Divide by 0.7563.
And where is that going to go?
Underneath the natural log.
Yeah, so it's outside the entire natural log. Because again, once I've taken the natural log, everything else has to be outside of that. So we're going to plug all of that in to our calculator. You do have a natural log, but just make sure you end your parentheses after the natural log. And what do we get? Point.
0.03958.
So 4. Yeah. Okay. Alright, now is that my answer?
No,
No, what does that represent?
billions.
Not
That-
quite. S is in billions. T is in Years.
Plus 2000.
since 2010. So this would represent,
2026.
and so that 2016
Right.
would be our answer.
So you have to add that to 2010?
Add what?
Yeah, you
I
said
added
since
six.
2010.
So T equals 10 corresponds to 2010.
So it's years since 2000.
8.
Yes. Sorry. Say yours since 2000. I said 2010. Oh, my fault.
Would that be right? 'Cause it has to be less than 14.
Yeah, so that's why it says according to the model. So according to this model, it would have been 2016. But because it's after that 2014, it might not be super accurate. But that's what it is doing. Other questions? Okay, so get another example. Says in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. The experiment starts with 33 flies. After 2 days, there are 100 flies. How many flies will there be after 5 days? So this time it tells us that we are using our exponential growth model. So that was the y equals a to the times e to the bx. So y is representing our population, x is representing our time. Eventually we want to plug 5 in for our time, but notice that right now I have an a and a b that I can't do anything with until I solve for them. And that's why they gave us some additional information. So if I have 33 flies, because again, y represents population, okay, at what time did that happen?
Day 0.
Day 0. So I would have b times 0. Well, what is b times 0?
0.
And e to the 0 is going to be
0. Or 1.
1. So I just end up with a equals 33. So your a is actually always going to be your initial population. So in this case, they gave us our initial population is 33. But we still have a b value that we have to find. Yes? And again, I need to find the b so that I can plug in 5. Do they give us any other information?
After 2 days, there was 67.
Okay, so what do I want to plug in where?
B times 2.
Okay, and then I want to set it equal to
100.
100. So again, I have an exponential equation. What do I do to solve that?
Divide by 33.
Okay. And then,
Unlog everything.
not common, but
Natural log.
natural log.
Between both of them.
It's okay. And then lastly, we would divide by
2.
Drop the 3 there. And again, I would plug that into our calculator. This time, since we are needing this b value to plug into our equation, we are going to go ahead and round there. So what do we get?
Zero.
So now we can plug both of those. So I have 33e to the 0.554x. So now what can we do?
And then we can plug it in 5 days.
And then we can plug all that into our calculator. And what do we get? Do we know it?
526.63.
526 point what?
635.
6 what?
63.
5?
5.
Now what's our unit here?
Flies.
Flies. Do I want 0.63 flies? Probably not. So we are going to go ahead and round to the nearest whole fly. So we would get 527 flies. I guess you technically have part of a fly, but we don't really want to deal with that. So, what questions do we have there? So let's look at one last one of our logarithmic models. So this is the Richter scale. It measures the magnitude R of the earthquake intensity I. I'm not quite sure why they put it this way, because really at the end of the day, I sub 0 is 1. So we just end up saying that this is log of I. Because if it's divided by 1, then it's just I. Okay? So then find the intensity of each earthquake. So R is 4.0. So like this is my Richter scale rating. So I'm going to plug it in for our R. This time we have a log equation. What's our base? 10. So how do I undo log base 10?
Exponential.
Put both of them to a power of 10. I'm not
And she
putting
by
a 10, yeah, as the exponent. So then, what happens to our log and our 10?
They cancel out.
They undo each other. So then I shove 10 to the 4th equals I. What is 10 to the 4th?
10,000. That was a yes.
It's
Right.
10,000.
It is 10,000. Okay? So, notice on part B, yes, we would end up with a very similar answer. Agreed?
Yeah.
But instead it's going to be 10 to the 7.8. What is 10 to the 7.8? It's a
really
big number. What is it?
0.09.
Hold on, 6?
6,309,000.
Nope, 63 million.
95,734.
734.45.
4.45.
Alright, and so notice, if I'm talking about an earthquake in Nepal, right, what I want to have to say, the intensity of that earthquake was 63,095,734.
No.
No, which is why it's much easier to say, oh, that was a 7.8 on the Richter scale. Yes? So the same thing is true when we use like decibels, right? So this is measuring wavelengths of your earthquake. Decibels measure sound waves, which again is why we want to convert them. Okay? So, what questions do we have on our log models?